Okay, in the miscellaneous topics, the next topic is the input offset voltage. Um, if we have an op-amp and we connect in a op-amp circuit, if we connect both the inputs, we expect the output voltage to be zero. But in practice, this is usually not zero. This is when it is not zero, whatever that voltage is known as offset voltage. Offset voltage. Now the input voltage required to make VO equal to 0 is called input offset voltage. And you can see the typical op-amp table in the book, for example, that this input offset voltage is usually of the order of millivolts. Very small voltage at the input is required to offset the output and get a zero there. So it is not related to our solution of op-amp circuits, but you should just know that what it is. Okay, and the other important thing, this is input offset voltage, and one of the other things that is not related to us in this course right now, but let me just make you at least familiar with the term. There is an important characteristic of op-amp and known as slew rate. Slew rate is usually the rate at which the output changes with time, with input actually. The rate thing covers the time. So it's usually measured in volts per time units, sometimes volts per microseconds. So for example, for mu a 741, the typical value is 1 volt per microsecond. What does this mean? I will come to this later. So the input offset voltage for mu a 741, for example, is 1 millivolt. Oh, I think this is 1 millivolt. This has some value. Let me look at this value. It is, sorry, it is 0.5 volts per millisecond per microsecond. What does this mean? This means that the output of the 741 op amp can change by 0.5 volt only in 1 microsecond. So the input should not be varying too much, so or at a faster rate that the output cannot follow it. So if the input is, say, a signal like this, where the input is changing at a slower rate. So this is a large time, for example, say this is 1 second, or this is 2 seconds, or whatever. And then if this is the input, the corresponding output would be, let me draw the corresponding output here. The corresponding output may be an amplified version of the same thing, and it can very easily track this output because it is changing at a very slow rate. So this is a lower voltage, this is a higher voltage. That's right. But if we have the same kind of input, but now this is, say, 1 microsecond, and this is a time in seconds, VI in volts, and this is now the time in microseconds. So the input is similar in shape, but it is no longer changing very slowly. So this change, this pulse basically occurred in 1 second, but now this is occurring in 1 microsecond. The output may still be able to follow it, but if we change this to, say, nanosecond, now this is a very fastly changing input. The output may not be able to track the input just like this, and we may get something like this. So it tries to follow it. It may even get delayed. uh, it tries to follow the input, but it cannot follow the abruptness with which the input changes. So as you see, the output is no longer like the input, and this is because of the slew rate. So with slew rate, we can know the frequency at which the output would be still reasonably be able to follow the input, or the rate at which the output can follow the input, or the how accurately can the output look like the input if the input varies with time. This is slew rate.